This video is about modeling with quadratic functions. For our notes, we're actually just going to recall all forms and characteristics of quadratic functions that we've been using recently, so I'm not going to recopy them all here, but we'll be using them in some examples in this section. Let's consider an example which reads as follows. A rancher with 2,000 feet of fencing wants to enclose a rectangular pasture for cattle which has one side bordered by a river. We want to do two things. First, we want to create a function to model the area of the pasture. Let's take note about which measure we want here, area. And then we want to find the dimensions which would produce the maximum area of the pasture. Now, the word maximum should be familiar. Lately, we've been discussing how to find the maximum value of a quadratic function, and there are a couple different forms we can use for it. So that'll be brought into play here. But we also have to consider that we're looking to maximize the area of the pasture. Now, it's usually pretty useful to get some kind of picture going for a word problem like this. And if we can recall, we need a rectangular pasture, but one side is bordered by a river. Okay, now we don't have to be an artist, but let's draw some kind of river and then a rectangular pasture that would be next to it. So we have some waves here in the river. All right, so we have a rectangle where three sides are the fence and then one side is the river. Now, we don't have any actual labels on this yet. We're going to throw those in here. All we have to be careful of is to make sure we can use whatever we label this thing with to make an equation. Now, if we want to maximize area, and actually that's what the first part asks us to model, that's what we're looking for an equation of. Now, the shape that we're working with here being a rectangle will have us recall that for the area of a rectangle, it's simply length times width, or sometimes seen as base times height. But that's all we know and need to know for the area of a rectangle. But now let's put some labels on this rectangle. If I call one of its sides x, I'm just going to pick the bottom side of this rectangle as we have drawn and label it x. Of course, given that opposite sides of a rectangle are equal, that means the top would be x as well. We could label that just to be clear. We don't really have to, but we could. And then the other side that would be now parallel to the river, that's still the fence, would not necessarily be x unless this turned out to be a square, which we don't know at this point. So we need to call it something else. Now, it's very tempting just to call it y or some other letter. And that's not wrong, except that it's going to become more difficult to have two different variables going on our picture. Because if I were to try to create a function to model the area, so if I said area equals, and then knowing that it's length times width, I could say x times y, but now I have too many different letters at play. So instead of calling that vertical side y, instead we're going to use what we know in the problem already, which is that the rancher has 2,000 feet of fencing available. Now, think about this for a second. We're fencing in three sides of this rectangle, and we're going to use up probably all the fence so we can make this thing as big as possible. So if we've already used x here and x here, the top and bottom of our rectangle, how much fence is left for this other side that's parallel to the river? Well, it would be the total amount we started with, 2,000, minus what we've already used up, which was x and x, so we could say minus 2x. So that would be the way we can represent the vertical side measure of this pasture area, this rectangular pasture area, which means, now notice, both the width and the length of our rectangle are defined in terms of the variable x, which means we can create an area function and call it a of x. And area is length times width. Well, we can just multiply these two measures together. So I'll say x times 2,000 minus 2x, which is just multiplying the two side lengths of our rectangle as labeled together. Then we could distribute this x and rewrite this as a of x equals 2,000x minus 2x squared. Now this might start to look a little familiar And it'll look more familiar if I rewrite it one more time, but put it in descending order. So I'm going to put the squared variable term first and make this negative 2x squared plus 2000x. This is what we have been seeing and calling general form. We've been using a couple different forms of quadratics, but this is a general form quadratic function. Now, the whole point, that takes care of part A, but the rest of this, the whole point is to figure out how we can maximize or find the maximum area for the pasture. Well, we've just been maximizing and minimizing quadratic functions as parabolas, and that's exactly what we want to do for this one. So let's call this second part B, and we want to maximize our function a of x. Well, if we take a look at that function, which is given right here, as we've already said, a of x equals negative 2x squared plus 2000x, then we can recall that this is all making sense because the leading term is negative 2. So in other words, remember looking at our a value, a is negative 2, and if a is less than 0, that means that the parabola opens downward, which means its vertex is a max. So this is actually looking good or looking correct so far. Now we actually want to find that max value, and we'll just consider that this is already in general form, and let's just leave it there. We have a way to do this. We know that the x-coordinate for the vertex in general form is negative b over 2a, and so we'll plug in the values we have for that. Negative b is, in this function, given as 2000. So we have negative 2000 over 2 times a, and we've already said a is negative 2. So we'll simplify this. Of course, it'd be negative 2000 over negative 4. Negative over negative is positive, and 2000 over 4 should be 500. And so our x value of our vertex is 500. Now we know we can find the y value of this vertex simply by plugging in our x value to the equation. In other words, we now want to find a of 500. And we already have a written above, so let's just copy that down. This would become negative 2 times 500 squared plus 2000 times 500. Now, if we were to compute this number, let's just think about what it would be representing. It's a fairly large number. I mean, you could just crunch it out on a calculator and get something for it. It turns out to be positive 500,000. Now, if we go back up and recall what the units are in this case, it was given as 2,000 feet of fencing. So we could say 500,000 square feet for the units of this area. Now, remember, that's the actual area that we now know would be maximum. And we know it would be maximum because of all the stuff we just discussed with the parabola and its graph. But look back at how the question is worded. For part B, it said simply find the dimensions which would produce the maximum area. So they actually weren't even asking for the max area, though we did find it, but rather just the dimensions. So let's go ahead and review or to summarize our dimensions now. Dimensions would be the length and the width. If you go back to our drawing, that would be the x times the 2000 minus 2x. Okay, so if we found x to be, earlier that was the 500 value, then our dimensions would be 500 feet by, the other measure was 2000 minus 2x. Well, if x is 500, then 2000 minus 2x would be 1000. So 500 feet by 1000 feet would be our max area dimensions for this pasture.